Good morning, everyone. Welcome to Turbulence. Today we are going to close the lecture on scales of turbulent motion. And last time we left off where we were going to do a problem from the problem at the end of the chapter. So I'd like to do that problem for you, and then we'll begin a new chapter. For homogeneous and statistically stationary turbulence, the energy spectral function for the inertial subrange can be given using a power law. So energy as a function of wave number kappa is equal to constant A times wave number kappa to the power of minus P. We want to show that turbulent kinetic energy and the dissipation rate over specific ranges of wave number are as follows. So I would like to show turbulence kinetic energy in a range of wave numbers starting from kappa to a very large wave number is equal to this expression. Likewise, I would like to show that the dissipation rate in a different range of wave numbers, that is from 0 to kappa, is equal to this expression. So we're going to do problem 4. So let's write out for homogeneous and statistically stationary turbulence the energy spectrum function for the inertial subrange is given as E kappa equal to constant A, kappa to the power of minus P. You must be careful that it's only in the inertial subrange that this expression holds, not everywhere. So to get the turbulence kinetic energy, now this is not kappa, this is lowercase k. In a range of wave numbers from kappa to infinity is just the integral of E kappa. Limits of integral kappa to infinity. Just note that I put kappa star in the integral because kappa star is just a variable of integration. It's different from the lower limit of the integral kappa, so I clearly have to distinguish between these two variables. It would have been a very lousy notation if I used kappa in both places, so if possible I must avoid confusing the variables. So now I'll substitute the expression. And this integral I know how to do. I have to evaluate this from kappa to infinity. So if I put infinity here, it's 0 minus A over minus P minus 1 kappa to the power of minus P minus 1. So if I get rid of the minus signs, this is what I am left with. So A divided by P minus 1 kappa to the power of minus P minus 1. So I arrived where I was asked to. What about the dissipation rate? If I have a different range, I must evaluate the dissipation rate, so I carefully write the expression for that. Different integral from 0 now to kappa to nu kappa to the power of 2a kappa minus p d kappa. So again, I put a star to distinguish the variable of integration kappa star from the limit of the integral. Now the higher the limit of the integral. So I bring the constants out to a new 0 kappa, and I'm left with kappa star minus p plus 2 d kappa star, and again I know how to perform this integral. Now this time if I put 0 here, I get 0, and the limit is equal to a nu 3 minus p kappa to the power of 3 minus p, which is what I was asked to show in the problem. So note that P must be in a range which allows evaluating this integral. So if I put a 0, well, I can't divide by 0, so P should be at most 3. You see what's happening? So when I put 0, I get 0. If its P is more than 3, then I get an undefined integral. So I have to be careful about the range of P where this integral is valid and can be calculated. Okay, so that closes the chapter on scales of turbulent motion, and now we shall continue with the following chapter. So chapter 8 is time and frequency domain. And it's another one of my favorite chapters, although not as much favorite as the last chapter was. I keep my promise. But this is, let's say, my second favorite chapter. So physical phenomena that are represented as a function of time, like anything you measure as a function of time, can also be represented as a function of frequency. In other words, I can not only analyze a system in the time domain, but also in the frequency domain. But you won't do this to any type of phenomenon. You do it to phenomena that exhibit some sort of repetition, because repetitions come and go at different frequencies, and that's when it's the most useful to analyze a system in the frequency domain. And we know something about eddies. Eddies come and go in turbulent flows with given rates of repetition. That's why it's so useful to analyze turbulence problems in the frequency domain. So this is true since most time-evolving phenomena exhibit various repeating patterns that occur at various frequencies. The frequency domain is therefore a description of such repetitions that occur at different levels of strength, and of course at different repetition rates. Discrete Fourier transform. This is a very useful technique to analyze problems in frequency domain. From Fourier analysis in calculus, we know that any well-behaved continuous function can be described by an infinite Fourier series. In other words, you can describe any well-behaved function in calculus, differentiable continuous, by an infinite sum of sines and cosine terms. Sometimes even the continuity is not a requirement, but it's really very general. However, most turbulent signals that are measured and represented are measured at discrete sampling frequency. So which means that our job in turbulence analysis is easier because there is no sensor out there that can measure a phenomena infinitely fast. So you're only looking at very limited finite number of points in a measurement, in which case you don't even need infinite sines and cosines in the Fourier series. So your job is even simpler. In the case of discrete time series with finite number of points, we only need a finite number of sine and cosine terms to fit our time series exactly. And by doing so, we have successfully transformed the problem from time domain to frequency domain. So which is very good news. That means having only a finite number of points, you can do an exact transformation from time domain to frequency domain with only very limited number of sine and cosine terms. So let's show you how this can be done. I'll begin with a hypothetical time series. Let's say there is a signal. This could be humidity, temperature, velocity. Say I bring a sensor in this room, I put it here, and I start measuring temperature for 1 minute. I'll do the measurement. Temperature is a function of time. Let's say K is the measurement. So the 0th measurement, the first measurement, the second measurement, so K could vary from 0, 1, 2, all the way to, suppose I make 60 measurements. If I measure temperature over a minute here, at every 1 second, I'll have 60 measurements. But K would vary from 0 to 59. And the time interval for my measurements is 1 second. Delta T is 1 second. Well, it goes without saying that most good engineers and scientists start from 0. They don't start from 1. This time series fills an entire period of time equal to P, the fancy P, equal to the number of measurements times delta T. So if I multiply 60 by 1, I get 60 seconds. The idea is to represent this time series function in frequency domain as a sum of sines and cosines with amplitude f as a function of n now. So a, the subscript a, tells you I'm transforming the signal a, and now it's a function of frequency, not time anymore. What you need to know is f is not necessarily a real number. A frequency transformation of a time series becomes a complex number. And in fact, the real part of that complex number represents amplitude of the cosine waves, and the imaginary part represents amplitude of the sine waves. As I said, frequency is a function of number of cycles per time period, which means that n, for my purposes in this definition, is not in units of hertz or per second. Frequency, for my purposes, is the number of cycles per the time period I measure. Take the temperature measurement over 1 minute example. If I measure temperature over 1 minute and temperature cycles once, say start from room temperature, in 30 seconds goes up by 5 degrees Celsius, and again goes back to the room temperature in 1 minute, it did one fluctuation, one cycle. So one cycle per time period is n equal to 1. The FA is the discrete Fourier transform, and it's a function of the original time series k, and therefore we use the subscript for showing a, because it was the time series a that resulted in a Fourier transform of f. Let's spend a minute and define frequency. We said for our purposes frequency can be defined as number of cycles per entire time period of a signal, but that's not totally unrelated to the most conventional forms of frequency we know. If you want to convert this frequency from n to some sort of frequency f in hertz or per second, all you have to do is divide n by the period of the measurement. Okay, so if, for this example, if temperature took 60 seconds to do one full fluctuation, if you divide by the time period, 1 by 60 is 1 over 60 hertz. Well, this sort of fluctuation is very slow, so therefore it's 1 over 60 hertz. It takes for the temperature to fluctuate once a minute. Of course, you can go from f hertz to radians per second, omega, in which case you just multiply 2 pi by f. And again, all of the three express the same phenomenon, but in different units. So you should be able to go back and forth from any unit of frequency to any other unit of frequency you desire. Now, what I should say is, let's put some definitions. At frequency of 0, there is no fluctuation, there is no cycle. So that ought to represent the mean value of the signal. So n equal to 0 corresponds to the fixed value of the signal, which does not do any fluctuation. The fundamental frequency is associated with n equal to 1, and it means that exactly one wave fills the entire time period t. So if I get one full fluctuation per minute, and time period was 1 minute, that corresponds to n equal to 1. But more things happen. You could have higher frequencies corresponding to different harmonics of the fundamental frequency. That means you fit more and more waves in the same time signal. If n is equal to 5, this means that you exactly fit 5 waves or 5 fluctuations in the signal. So far so good. Okay, let's show you how the frequency transform is done. This is done using the Euler's formula. So we showed you that exponential of a complex number ix is equal to the cosine x plus I sine x. So this is the well-known Euler formula. I is here the complex number and x is the real value. You could use this to define the Fourier transform. If you take your signal ak, divide by n number of measurements, times exponential of this term minus I 2 pi n k over n, and you sum that over all values of k, then you have the forward Fourier transform. Be careful that this transform is a function of n. It's not a function of k, certainly because after I perform the sum over k, the dependency from k is removed, like all the k's disappear from this expression, and only n remains, which is on the power of the exponent. Okay? This is called the forward transform, and certainly if I now sum over all of the frequencies, now I'm summing over n from 0 to n minus 1, then I retrieve the time series signals, so I get what I started with. This is called the backward. So if you like, really, these functions are interchanged. And I can go back and forth indefinitely. I take forward transform of A, I get F. I go backward transform of F, I get A. And I can continue this indefinitely. So the first one is called forward transform, and the second one is called inverse transform. If the original time series AK is known, then F coefficients can be found from the forward transform. And as I said, I can go backward to the time series by doing the inverse transforms. To find the coefficients, all I need to do is to go forward. You seldom need to go backward because you already have the time series. You know what it is. There's no need to go backward unless you want to verify your calculation. So going forward is also known as Fourier decomposition. It's the same thing. But the profound result here is really we don't need infinite number of terms. We only need n terms. Because think about it. N, there's only, k is only 60 different values of k, so I only have a sum with 60 terms. So which means that my job should be very easy. I don't need infinite number of terms. In fact, if I have n number of measurements, I exactly need only n terms or n frequencies to show my Fourier decomposition. No more, no less. I'll show you an example. Suppose I have a time series signal. I'm measuring a specific humidity in the atmosphere. So that would be gram water vapor per kilogram dry air, although don't worry about the units. But let's say I made 8 measurements. I measured it at time 0 or noon. I measured it to be 8, then 15 minutes later 9, and every 15 minutes I repeated the experiment and I had 8 measurements. It goes without saying that UTC here shows universal time coordinate. But that's aside. By performing a forward transform, I can obtain 8 coefficients for the Fourier transform. So now f as used to describe time series signal q. Okay, so it's not f of a anymore, it's f of q. These coefficients can be shown as a sum of real and imaginary numbers. Of course, n was 8 in my example, delta t was 15 minutes. So the total time period is n times delta t, 2 hours, or 120 minutes. And the 8 coefficients that I calculate as a result of this Fourier transform are given in these formulas. Well, if you apply the Euler formula to the 8 terms, you have the forward transform that's possible to obtain using this sum. So that's the real part, k summing from 0 to n minus 1, and that's the imaginary part. So notice complex number I here. Of course, you can check your calculation and make sure if you go back, you do get the original time series signal. Now, I should say a careful statement about the backward or inverse transform. In fact, originally there was 4 different sums here. Well, why? Because going backward, f is no longer just a real number. In fact, going backward, you have to put a complex Fourier transform f here, and then by another complex number here. So you actually get 4 terms, but conveniently 2 of those sums would cancel out. The inverse transform sums are in fact 4 sums as opposed to 2 sums. The remaining 2 sums consist of real part of f times the imaginary factor I sine the angle, and the imaginary part of f times the real factor cosine of the angle. Because the last half of the Fourier transform are complex conjugates to the first half, these 2 sums identically cancel. That they only leave 2 sums to do. So it's a fortunate situation. The sum is has less terms. By performing the calculation of the above sum, it can be verified that the signal can be recovered, and you can check that. Well, I didn't show you the forward transform. That's what I'm going to do now. If you do the forward transform, for the specific humidity, the example I gave you, these are the terms you calculate. So as I said, you need only exactly 8 terms to describe all the frequencies for that show the physical phenomenon. So for n varying from 0 to 7, you get 8 different frequencies. These are complex numbers, and this is it. Now, can you notice a bizarre nature or feature of this table? What's bizarre here? The online viewer is right. It's bizarre that there's some sort of symmetry here. So you see some of these numbers repeat around the central frequency, 78, 78, 28, 28. Also the imaginary parts are symmetric with respect to these lines, like a mirror of those, although the sign is flipped. So there's some sort of symmetry here, and I will next try to explain what this symmetry is. Nyquist frequency. Almost all measured time series are discrete in nature because every measurement probe has a sampling frequency and cannot measure infinitely fast. So most often in the practical sense we deal with discrete samples. The rule of thumb in discrete data analysis is that at least 2 data points are needed per period or wavelength of a wave in order to be able to resolve that wave. So you're limited by the frequency of your measurement to describe frequencies or higher frequencies of waves that are in the system. You can only say so much. For example, discrete Fourier analysis involves decomposing the time series signals into waves of different frequencies. If we have a total of n data points with a constant sampling frequency, then the highest frequency that we can resolve in our Fourier transform is n over 2. This frequency is known as the Nyquist frequency, named after Henry Nyquist. Here's some example. If a wave period is 0.1 second, how fast should I be measuring the physical phenomenon to be able to resolve that wave? Well, I should be measuring twice as fast, which means that I need time series digitized at least every 0.05 seconds, so 1/2 of this period. I can make the same statement in the length domain. Let's say you're flying a moving probe into a turbulent flow. If a wavelength of a wave is 1 meter, and I want to measure that, the signal must be digitized at least once every 0.5 meters. Again, half of the wavelength, I should be digitizing the signal. Now, how does this relate to the symmetry in the Fourier transform? If higher frequencies of the time series are present, well, I cannot measure them due to the limited sample frequency. But those frequencies, higher than the Nyquist frequency, are folded or aliased. In other words, they are artificially measured and manifest themselves into the amplitudes of the lower frequencies, which I can measure. This is known as aliasing and folding. And I can show a picture of you of that phenomenon. Let me show you this concept of Nyquist frequency first. So Nyquist frequency. Suppose I have a time series, the same example I used, the temperature, and I start measuring temperature. I have a few temperature measurements. Here I deliberately put in a wave here as if this temperature signal fluctuated once over the time I measured, although I didn't make it perfect. But by and large, there is one fluctuation in this measurement. If I'm interested to detect a wave as large as the period of the measurement, let's say if I want to see there is a wave in this with that period of measurement, of course I can say with confidence that there is, because I can see a fluctuation here in my points. So there's definitely a wave with that period in this signal. What if I ask you if there's a wave of a smaller time periods or higher frequencies? Let's say if I only looked wanted to see if there is a wave in half of this signal. That means another period. Again, I can see that there's some sort of a wave in this. So at first it's positive values of that measurement and then negative. So there's definitely a wave here. The data tells me that. If I push the limit and go further and further down, let's say now I'm interested in only a period which is 2 times the sampling time. Remember, sampling time is time between the measurements, right? So the time between each subsequent measurement is sampling time. So if you like, every delta t seconds, I make a new measurement. Is there a wave with a period of 2 delta t? Again, if I have 2 data points, I can probably confidently say there's a wave here. But you'll see below this limit, it's very hard to say there is a wave. Suppose I only looked at that number, that measurement. It's very hard because maybe I can show, maybe I can say this is a wave, which is sort of a sine wave, or maybe there's a cosine in this. How would I know? It's very hard to know with one data point if there is a wave nature of fluctuations. So as you see my point, at least I need 2 data points in the time interval of interest to say something about presence of a wave there. That's the limit of periods, lower limit of periods, or higher limit of frequencies I can detect with this sampling frequency. Okay, so that's pictorially shows you what Nyquist frequency is. About folding, I'll also show you a picture to describe folding. So when you do Fourier transform, so aliasing or folding. When you do Fourier transform, in fact, you are calculating the energy spectrum function, because remember, you're going from time to frequency domain, and wave number is related to frequency. And this is the sort of the spectrum you get. Of course, the higher the wave number, the smaller the eddy wavelength should be. So this L, suppose, represents the length scale of eddies, and the higher the frequencies, higher the frequency. So that's what a large wave number should mean. Small wave number is a very large scale of fluctuation, a very large eddy, and a very low frequency. Okay, so when aliasing happens, it happens to the right-hand side of this curve. And if this is a true energy spectrum, if you could measure turbulence infinitely fast, you would get this. But in practice, you can't measure infinitely fast. So instead of measuring this, you would measure something like this. And this is up to which point you can measure. So basically, you couldn't measure these amplitudes associated with really high frequencies that your probe could not resolve, but those artificially manifest themselves in the range of frequencies you can measure. So this is artificially folded back, it's called aliasing or folding. And this is the limit of measurement. So limit of wave number measurements. So this point is associated with the Nyquist frequency, NF. Okay, so that pictorially, that's what happens to the signal if you do Fourier transform. You can't actually see very high frequencies there. However, those frequencies are actually there in the signal. It's just that I can't measure it. So what should you do? So there's a lot of techniques you can do to remove aliasing from your signal. You can use an analog electronic circuit that will perform low-pass filtering of the signal. So this will automatically remove high frequencies. So it's a piece of hardware you put in your electronics for the sampling probe. Alternatively, you can do a block averaging of the signal, time averaging of the signal. So if you time average your signal, then you would remove the effect of large, very high frequencies. So there's some techniques to remove that. So the next topic is the energy spectrum, discrete energy spectrum. And again, we've touched this before a few times, twice at least. But now I want to pick that up again and reinforce the concept. In turbulent studies, it is often desired to know how much of the variance of a fluctuating time series signals is associated with a particular frequency or range of frequencies. The answer to this question is possible using the discrete Fourier transform. The square of the norm of the complex Fourier transform for any given frequency n is given by this expression. So the norm squared of the Fourier transform is the square of the real part plus the square of the imaginary part. Why am I saying this? Because it helps to visualize any complex number in a two-dimensional plane, where the horizontal axis is the real part and the vertical axis is the imaginary part. So this could be f real, this could be f imaginary. So the complex number is actually here in the two-dimensional plane, and the magnitude of it is given by the Pythagorean law, because I have a right triangle here and I can calculate the magnitude. So this is the magnitude of the complex number f. And that's what we're doing here when we say norm squared, magnitude squared is the sum of the squares of the components. That's what we mean. Now, this is, however, sum over different frequencies. I mean, I can write this for any frequency of interest. The result of all of these sums altogether, it is the total biased variance of the original time series. And that's the fundamental connection between Fourier transform and the fluctuations in the flow. If you sum up the Fourier transform in squared, if you sum it up over all the frequencies, you will get the original variance in the signal. Of course, it's never possible to do a statistical variance or average, but the variance for the time averaging that you are obtaining. You must note that the square of the norm of the complex Fourier transform is summed starting from 1 instead of 0. Can anybody answer that? Why is this sum starting from 1 but not 0? Why am I neglecting the first term? Yes, again, the online viewer is right, because n equal to 0 is associated with the mean value or average. The mean value or average of a signal does not contribute to variance. Variance is resulted by fluctuations. So I need to start from the first harmonic and so on. We can interpret this Fourier transform norm squared as a portion of variance explained by waves of a given frequency n. And if desired, I can sum it up over a range of frequencies to get the variance for a range of frequencies. Say variance for a range of frequencies from n equal to n1 to n equal to n2. I just sum up all these terms over those ranges of frequencies. For frequencies greater than the Nyquist frequency, there are some problems. I couldn't measure them, remember? I said I couldn't measure them. Then these terms are identically equal to those at the corresponding folded lower frequencies, because the Fourier transform of high frequencies are the same as those of the lower frequency, except for a sign change. Frequencies higher than the Nyquist frequency cannot be resolved by the transform. So these values are at high frequencies are actually folded back. These are the values that are artificially measured. So again, going back to the example I showed you, I'm talking about the folded values. The reason I get asymmetry here is because of the limited Nyquist frequency. So Fourier transforms above and below the Nyquist frequency are symmetric. Therefore, the discrete spectral energy or discrete spectral intensity or discrete spectral energy is handled with special care. And this is what I mean. So, discrete spectral energy is defined as 2 times the Fourier transform, because remember, I can only go up to NF. I can't go beyond. So I still have to account for the missing part. So therefore, I have to consider twice of this. Okay. However, the care must be given here. If the number of measurements is odd, it's simple. I just multiply all of these by 2. Done. But if n is even, the symmetry line doesn't land on a frequency. It lands in between 2 frequencies. Okay? So I have to double the Fourier transform norm squared for frequencies up to the frequency before the Nyquist, and do not double the frequency, the norm squared at the Nyquist, because this one was not mirrored. Okay, so that's the delicate point here. So if you have a signal, you have to carefully look at the number of data points. If it's odd, you treat it differently than when it is even. Okay. So far, so good. Maybe you are thinking, yeah, if I always just try to get exactly odd number of data points, my job is easier, and I agree it is. I mean, let's say if you get 2,000 measurements, make it 2,001 measurements, or 1,999. So you don't possibly make a mistake by a special treatment of discrete transform at NF. So that's maybe a practical tip. The next topic is discrete energy density spectrum. Related to the concept of energy is energy density. If you divide discrete spectral energy by the width of two frequencies of interest, delta n, then you get the spectral energy density. So that's the definition. So you go from E to S, which now has the units of A squared per unit frequency. The advantage of spectral energy density is that instead of summing the discrete spectral energy over a range of frequencies to find a variance, you can instead take the integral of the spectral energy density. That's why densities are useful, because once you divide a quantity by the width of the distribution, then you can integrate that function, whatever it is, polynomial, inverse, sine, cosine, logarithmic, exponential, you can just integrate that to get the variable of interest. In this case, the integration is variance over a range of frequencies. But in probability statistics, we do the same thing. When you have the probability density function, PDF, its PDF is made exactly because you can integrate it to get probability of events happening. So same idea here. So oftentimes we don't work with discrete energy, but we work with spectral energy density. And the example we showed you, this can be done. So let me put the example up again. If you perform a forward Fourier transform of the original time series, in that case, you had 8 measurements. So these are the Fourier transform, complex numbers. The 0th term was associated with mean. So 7 was the mean or average of all the 8 measurements. That does not contribute to any variance. Then fluctuations come, the first harmonic, the second, third, the Nyquist frequency, and that's the symmetry line. And then I've got the symmetries around this, okay? 78, 78, 0.5, 0.5, and so on. If I take the norm squared, okay, so that's a square of this complex number, right? So a square of that is here. Square of the complex number, magnitude squared is that one. Then twice that is discrete energy, right? Twice that, because I have to account for the missing parts also. So I twice these, except for the Nyquist frequency. Remember, for this case, I have 8 measurements. So Nyquist frequency, I don't double that. I doubled the squares here, but I did not double it here, right? Because the symmetry line goes over this point, right? One itself has no symmetry, it's on the symmetry, right? But let's say in the case I had odd numbers, then the symmetry line would be here. Even Nyquist would have been mirrored up or down. Okay, so I didn't double this. If I add all these up, I get the sum, which is the total variance of the signal. In this case, spectral density is the same as energy, because delta n is 1, right? Frequencies jump over by 1 unit. So this divided by delta n, or 1 is itself. But mathematically speaking, these are different quantities. This is discrete energy, that's spectral energy density. So you have to be very careful. I should next discuss another important topic, and that's a spectra of 2 variables. might be thinking all of the discussion so far on a spectral analysis only concerned one of the components of fluctuation. Let's say fluctuation of U, or variance of U, or V, or W. Only a single component of fluctuation. You may be asking, can Fourier decomposition or frequency domain be used for a pair of fluctuations, or the covariance? And the answer is yes. We do it all the time. In turbulence studies, it is often very useful to analyze the spectrum for a product of two fluctuations. For instance, the product of the fluctuations of velocities in some directions E1 and E2 correspond to U1, U2. Think of like X and Y directions, you get U and V. X and Z direction, you get U and W. The cross-spectrum analysis relates the spectra of two variables. Okay, now I need to get another concept established before I can make full sense of the cross-spectrum. I want to talk about the idea of phase now. The phase relates to the position within one wave, such as the crest or trough, and is given as an angle. Okay? Well, why phase? Well, because all the waves are described by sinusoidal fluctuations from the point of view of Fourier techniques. So we need to be comfortable with the idea of phase. A phase shift refers to the angle between one part of the wave, such as a crest, to that of another wave. The concept of phase shift comes up all the time when you look at two waves with respect to one another. And now we need to do it because we are talking about two components of fluctuations. And supposedly, these are two different waves. Like U is fluctuating, right, in this direction, and V is fluctuating in a different direction. So when you start talking about two waves, immediately you have to start talking about phase shift to understand if there's a shift between the peak or trough of one wave with respect to another. Okay? For example, I have two waves. Wave number one at this frequency, this looks like that, and another wave looks like that. If you like, the peak and trough, the crest and troughs are in sync, the time sync. There's no shift. When the first wave peaks, so does the second wave. When the first wave goes to the trough position, so does the second wave. But not always. I mean, for example, at higher frequencies, for the sake of argument, the first wave may be doing this. However, the second wave may be shifted. Right? So the second wave is shifted by some amount. Now, I deliberately changed the amplitude of the second wave, right? It doesn't need to have the same amplitude. I deliberately did that. And I expressed phase shift as a function of frequency. Again, deliberately, because there are different frequencies for each wave. If you do Fourier decomposition, you're talking about a bunch of frequencies. So there may be no phase shift for one frequency. It's a low frequency here between the two waves. But for a high frequency, there may be a phase shift. So you can see it can get complicated for different waves, different frequencies between the two waves. There might be different phase shifts. The equation for a single sine wave of amplitude c that is shifted by some angle phi is given by this. Well, oddly, I am now expressing the time series as both function of time and frequency. Well, now I'm allowed to do that because I'm only looking at a sinusoidal. I mean, this is a simplification. Supposedly, this is the time series for the wave corresponding to frequency n. Okay, so that's after the decomposition. The phase shift appears as a shift in the argument of the trigonometric function, right? So this is a shift in the argument of sine, so phi n. In this equation, k index signifies timestamp, i.e. represents a particular data point of a time series, while n is a measure of the frequency of the wave. The same equation can be shown as the sum of the sine and cosine waves. Why? Because using trigonometric identities, you can break this sine of a sum of the two angles as a bunch of sines and cosines. If you do that, then new amplitudes come up. The amplitude for the cosine part is now a function of phase shift. So is the amplitude of the sine part. The amplitude is no longer the same amplitude, but it's being changed by cosines and sines of the phase shift. The Fourier transform gives the amplitude of sine and cosine terms in the spectral decomposition of the original time series. Therefore, we can also interpret the spectra in terms of amplitude and phase shift. Now I'm saying something even more profound and deeper. Fourier transform not only tells you the strength, level of strength between different waves in there, i.e. the amplitudes of different waves at different frequencies, but it also tells you if some of those waves are shifted with the other waves, especially if you're looking at two components of fluctuations. If you're looking at two waves, then Fourier transform also tells you something about the shift in the phase between the two waves. So we do a bit of a couple of more definitions, only semantics. We can define G as the norm squared of the Fourier transform. I mean, I just want to have new definitions. The same thing, it's nothing different. Norm squared. But remember, it's still a function of n. However, for simplicity, I dropped the dependency on n for the next page or so. But remember, it's still a function of n. So this is for short as the unfold spectral energy of a variable a and frequency n. We can write G as follows, as Fourier transform variable itself multiplied by the complex conjugate of itself. In other words, I'm saying if you take a complex number multiplied by its complex conjugate, you get the norm squared of that number. And I'll show you briefly. This is one of the properties of complex numbers. And one can quickly show it. Can be shown by considering the real and imaginary parts of f. If you show any complex number f of time series A is the sum of the real part, FAR, plus IFAI, the imaginary part. Again, subscript R and I signify real and imaginary parts. So what is a complex conjugate? Remember, if you have some complex number, like A plus IB, the complex conjugate of that complex number C is A minus IB. So you just flip the sign of the imaginary part. That's the conjugate of that number. And that's what we're doing here. If you multiply complex conjugate of f by itself, you carry the sum, you will realize quickly that two of these would cancel. So these two terms will cancel. And in fact, minus I squared is equal to 1. It's the property of the complex number, imaginary number. So you get the square of the components of the complex number. Well, it must be the norm of A squared. So now we're going to take it a step further. Now I want to define G as one Fourier transform of one signal that I had times the complex conjugate of the other signal. Think of it this way. This could be the Fourier transform of U component of fluctuations times the complex conjugate of the Fourier transform of the V component of fluctuations. I can do that. And I want to define it and work it out. If you work this out, an interesting thing happens. You will get two real numbers, so that's a real number. This is also a real number because I squared is real, but then you get two imaginary numbers. Now if you collect the real parts and the imaginary parts, you get the co-spectrum and the quadrature spectrum. Basically, co-spectrum is the sum of the real parts, and we show it with co, and quadrature spectrum is the sum of the imaginary parts. We show it with q. Of course, I factored I out of the imaginary parts, so q does not contain I factored I out. So again, this is co-spectrum. It's the product of real part of A, real part of B, plus the product of imaginary part of A, imaginary part of B. Quadrature is real part of A, imaginary part of B, minus imaginary part of A, real part of B. Again, all of these are frequency dependent. This is actually co-spectrum at frequency n of f of AR at n plus times f of BR at n. Every term here depends on frequency. But I just dropped it for brevity of notation. It again must be still remember that everything is a function of frequency here. Why did I do that? I did this because the co-spectrum and quadrature spectrum are very important. They have very deep physical contents. First of all, quadrature spectrum tells you about the phase shift between the two signals, but more importantly, the co-spectrum is related to the covariance of the two signals. And that's the fundamental connection. The co-spectrum is frequently used in turbulent studies because the sum over all frequencies is equal to the covariance of the turbulent fluctuations A and B. So if you sum the co-spectrum over all terms in frequency, you will get the covariance as was time averaged. So you could calculate, in fact, all the components of Reynolds stress, UV, UW, VW, also in the frequency domain. Not only that, you can look at the components of covariance associated with a range of frequencies. You can do all of that. Be careful. For spectral computed this way is not equal to the spectrum of time series of the product. Well, time series of the product is a different beast. Okay? Time series of this is a different beast. I'm just saying for spectrum relates to covariance of the two fluctuations. So you can see in the frequency domain you can do everything. You can analyze all the fluctuations, whether it be normal or shear components of the Reynolds stresses. You can understand which strains and phase shifts exist in these components of Reynolds stresses. You can also look at any variable of interest. It doesn't have to be related to momentum. You can look at fluctuations in temperature, fluctuations in passive scalar, or fluxes, or a combination of momentum and temperature fluctuations. You can look at basically any fluctuation in the frequency domain, and we do it all the time in turbulence studies. Let me do one problem from the exercises. Before that, are there any questions? I'd like to do exercise 1. A time series has a period of 15 seconds. This time series is composed of numerous harmonic frequencies. You want to calculate the third harmonic frequency, i.e. n equal to 3, in units of cycles per second, which is f, and radius per second, which is omega. So let's do this very short problem. Example 1. The time period is 15 seconds, and I'm interested in n equal to 3. Well, f is equal to, by definition, n equal to p, which is 3 over 15, which is 0.2 hertz. Omega is, by definition, 2 pi f, which is 2 pi times 0.2 is 0.4 pi. Now the unit is radians per second. I can also pictorially show you what these harmonics mean. If the period of measurement is 15 seconds, that's associated with no fluctuations, n equal to 0. N equal to 1 is the case where I have exactly one fluctuation in this period, so that's the first harmonic. The second harmonic, I should fit 2 fluctuation, that's n equal to 2, and the third harmonic is the case where I fit 3 fluctuations, and it just goes on. I can look at the 4th, 5th harmonic, all the way so on. So pictorially, that's what we mean by fitting one wave in an entire time period, or 2 waves in the entire time period. Okay, so far so good. Any questions? Well, this is an exciting time because we have finished the first part of the course, which was the fundamental understanding of turbulent processes. So that part is now done, and from next chapter on, we'll begin part 2, which is turbulence modeling and simulation, which is another exciting part to investigate. So thank you very much. We'll see you next time.